This is brought to you by the Alumni Association of PISJ-ES.
Hey guys, so we'll be continuing our lecture on forces, and we'll be using the same Java applet that we used earlier. And the case that we'll be discussing in this example would be, what if only the friction force acts on an object? So, what if only the friction force is acting on the object? Now let's see, what are the cases here? For example, if this is the box of mass, let's say just mass m, and I am pushing it with a force, which is applied force, and this is, let's say, 100 newtons, and it suddenly starts to accelerate, the friction is acting in this direction, obviously opposite to the motion. Let's say the motion is in this direction, the friction is acting, and it moves a little bit, and I am just pushing, I'm continuously pushing it till this point, and after this point, while it's moving, I'll just stop pushing it. I don't push it anymore. I just leave the box, and just to see what happens. So at this scenario, when I leave the box and I'm not pushing it anymore, there is no applied force, and it will already be moving with some velocity, let's say 10 meters per second. I don't know, but this might be moving at 10 meters per second, let's just say. So what happens? The only force that will be exerted in this case would be the friction force, which would be trying to stop this motion. It would try to bring it to rest, because there is no applied force, so it would not continue moving, since the applied force just stopped at this point, I'd just say some time. So at this point the applied force became zero, so the only force that was acting was the resistive force, or the friction force. So what happens is that friction force tries to bring it to a stop, and we know that if we push, let's say, a box on the table, no matter how slippery it is, it will eventually come to rest. That is because the friction force is only acting on it, and the friction force is trying to slow it down. So we'll see in our Java applet, and we will see what happens if the only force acting is the friction force. So let's see, we have we have the file cabinet here again, and the friction is here. Let me see, I am applying, this is my applied force. I can also apply a force like this, and you can see the applied force is changing over here. When I do this, the applied force changes. So you can see the applied force and friction forces are changing, and you will learn in the later lectures that the friction force will increase with the applied force as well, as in it comes to a maximum value after which it cannot increase. So let's see the applied force. Let's take it down to 600. 590, it starts moving. So here starts moving. You can see thing going on. Right now, suddenly, if I just stop it, it would come to stop. You see, it just comes to a stop. Let me just make it clear again. Let me just clear the data, and let me just take it to a constant, say 790, and I suddenly stop. I suddenly stop the applied force. So what happens? The friction force is the only force acting on the opposite direction, so it makes it come to a rest. So let's see what happens when only the friction force is being applied. First, let's see the graph of acceleration. What happened? In the earlier stage, the acceleration at this point was 2 meters per second square. Alright? So the acceleration at this point was 2 meters per second square. And suddenly you can say there's change in the acceleration, and the acceleration became negative. So let's see what exactly happened here. Let me just do this, and we'll just note the values when we'll be doing this again. So let me just clear this. So I will take a constant value here, say 800. So at the applied force of 800, and then I leave the applied force, and you see that it comes to a rest after say 18.8 meters. So this is the graph. Initially, when I applied a force of 800 newtons, the acceleration was 2 meters per second square. Now let's see what the friction force was. So let's find out. We know there was a friction force. So in our example, the mass of the cabinet was 200 kilograms, and you can see from here as well, this is the cabinet and the mass is 200 kilograms. The applied force in this case was 800 newtons. So this was the scenario here. This was the mass, this was the applied force of 800 newtons. However, there was a friction force acting in this direction, but it was still accelerating. And we know the acceleration for the first part, where there was an applied force, was 2 meters per second square. So the acceleration is 2 meters per second square. So let's find out the friction force acting on this box so that we can use it later. Let's see, the friction force on this box would be, so for this we'll have to find out F net is equals to MA. The F net would be, let's take this side as positive and this side as negative. So the F net is in this, the force applied is in this direction. This would be positive 800 minus the FR in the opposite direction. We took this direction as the negative direction. Is equals to mass, which is 200, times acceleration, which is 2. This becomes 800 minus FR minus friction force is equals to 400. Now just switch the formula and make FR the subject. This becomes 800 minus 400, which is 400 newtons. So the friction force on this cabinet was 400 newtons, and this will stay constant as long as we are moving the same mass and on the same ground, on the same floor. So yes, in the next example we'll only be using a cabinet, and we'll only it will be on the same ground. So this friction force would stay constant. Now we found out the friction force. Now let's see what happens when we stop the applied force. Now what happens? At a time I just stopped, you just saw I stopped the applied force. I stopped applying a force. So at that instant, what happened? That there was the mass, which was of 200 kilograms. And the net force, the only force that was being applied, was in this direction, in the opposite direction. However, the velocity was in this direction, because it was moving in this direction. The velocity was in this direction, but the net force was in this direction, because friction force was the only force being applied to it. There was no applied force. So friction force was the only force that was being exerted on this mass. So we know from our graph that the acceleration at that time is minus 2 meters per second square. You can see this is minus 2 meters per second square, which means because our observation said that this would be positive earlier and this would be negative. So from our observation, a minus 2 would mean that the acceleration was in this direction. It was accelerating in this direction at 2 meters per second square, because it's a minus sign, so the arrow should point on the left hand side. The acceleration was in this direction. Now we know the friction force. We know the friction force. The friction force was, let's say, what was the friction? The friction force was 400 newtons. Now, I would, when I have all this data, I would see after what time it actually. Let's just find this value first. Let's suppose we don't know the graph. Let's just find the deceleration, because obviously this is moving in this direction and this is trying to stop it, so it would not accelerate. Obviously, it would just decelerate. It would slow down. So let's see how we'll find the acceleration. Would simply be again F net is equals to ma, but this time the F net would be minus 400 because it's in this direction, and the mass is 200 kilograms times acceleration. So acceleration is equals to 400 minus 400 divided by 200. This would give me a minus 2 meters per second square, and this would show me that it's coming here and towards the left hand side. Now if I want to find out, let's say, the velocity, the velocity that it had attained before, as in it had attained at the point when I stopped applying the force, the velocity it had initially when I stopped applying the force. So if I want to find that out, let's say I know this velocity, let's say I know this initial velocity at which I stopped applying the force. This was this, and we can see at this point, this was the point when I stopped applying the force. So this was around 4.5 something. Let's say this is the velocity, the time is 4.5 and the velocity is something like 7.9 something, or let's just take 8 meters per second. Let's just say that when it attained a velocity of 8 meters per second, I stopped applying the force, and the only force that was being applied was the friction force. Let's see how much time it takes to come to rest after I stop applying the force, and the only force that was being applied was the friction force. So let's say the initial velocity when these conditions started to apply, when as in the only force was friction force, the initial velocity at that point when I stopped the applied force was 8 meters per second, and the final velocity is 0 meters per second because I want to see when, the time taken for it to come to rest. So at rest the velocity would be 0 meters per second, and we want to find out the time, and the acceleration or the deceleration, let's say the acceleration is minus 2 meters per second square. It's in the opposite direction to the velocity, and the velocity is towards the right hand side, so it's all positive, and positive 0 is nothing. So now the formula that relates velocity and acceleration, v minus u divided by t, is equals to acceleration. Velocity, initial velocity, this is final velocity minus initial velocity divided by time. Final velocity is 0 minus initial velocity is minus 8 divided by time is equals to acceleration. Now to switch the formula, minus 8 over minus 2 is equals to time. So the time is 4 seconds. It took the object 4 seconds to come to a proper rest. Let's just see, obviously the answer would not be accurate because we used an 8 meters per second instead of a 7.8 or 7.9 that was stated there, but it would be pretty close to this answer. Let's see how much time it took to stop. So this started with a 4.5 or 5 point something, and it ended up at 8 point something. Let's say this is a 5 and this is an 8.5 or 8.6 something when it came to a 0 velocity. So 5 and 8.5, which makes it 3.5 seconds. So because we took some inaccurate values, we were close enough. We could show that this is 4 seconds.